Here's a quick mechanics problem which is actually similar to one that I did on the channel not too long ago. In that one, we had a frame and a collar within that frame, and that collar was at a certain angle with respect to the horizontal. Now, in this case, we've got a simple pendulum which is inside this frame or plate, as it's called, and then what happens in this instance is that we know that this frame has a certain acceleration upwards along the plane, and then we have to find this angle beta, which is the angle that the arm of the pendulum makes with respect to the normal to the plane. So we know a couple of things. We know the angle theta, right? So this is kind of given to us. We know the acceleration of the frame, and based on that, and obviously based on g, we have to find what the angle beta is. Okay, and this could be the kind of question that you might see in your first year engineering module, or it might be something that you can also see in high school. So if you'd like to see anything similar to this on the channel, let me know in the comments. So as usual, what I would do in this situation is I would draw the free body diagram of the pendulum. So I'm going to ignore the pendulum arm, and I'm just going to draw the pendulum bob, I guess I can call it, like this. And then I would write down what forces are acting on it. So first of all, we have weight, which is, as usual, acting downwards. So this is our mg. And then we have the tension, basically. So the tension is acting at this angle. So let's try to look at, so let's imagine this is the direction of the incline, right? And then we have this point, which is where the arm is attached, and then we've got this normal to the incline. And then the tension is going to be along this particular, maybe I should draw it a bit shorter because it looks like it's in the same direction as the weight, which it's not. So let's say that this is where the arm is attached, right? So we've got this sort of angle here, which is beta. Okay, and then we know the angle of the incline with respect to the horizontal is theta. Okay, and the other force that's acting on the bob is the tension force. So the tension force is acting along the arm, and it's pointing towards the pivot point, right towards that point that the question calls as just O. Okay, so that's all we know. And I think that's all we need in order to find out what the angle beta is. And the other thing, of course, is that this whole system is accelerating up the plane with an acceleration that's called just A, right? So because everything is stationary, it means every single point on the system, so it could be this one or point O, or it could be the center of mass of the pendulum. So every single point is accelerating with an acceleration of A in the direction, along the plane, climbing the incline. So after we drew this free body diagram, we can then write down the equation of motion. So actually, before we write the equation of motion, we have to decompose the forces, because those forces are sort of acting all over the place, right? We have weight, which is acting down, but then we also have tension, which is acting at that angle with respect to the direction of the incline, which is this angle right here. But that angle is pretty easy to figure out because this is a 90-degree angle, so this would be pi over 2 minus beta. Okay, and then this tension is going to have a component acting upwards along the plane, so that component is going to be t cosine of pi over 2 minus beta, which is the same as, according to trigonometry, is the same as t sine of beta. And seeing how the acceleration is acting upwards along the plane, we might as well just decompose all forces in a direction along the plane. So we dealt with this tension force, and then let's do the same thing with weight. So the weight has essentially two components. So it's got a component perpendicular to the plane. So this is the angle, this angle theta. This is mg cos theta, and the component that's acting along the plane is actually, acting towards the base of the plane, and that's mg sine theta. So, and that's all there is to it in terms of decomposing forces. So now we have two forces which are acting in the direction of the incline. We have one which is t sine beta, which is actually t cosine of pi over 2 minus beta, but trigonometrically it's the same thing. And then minus mg sine theta. So sine, or this force is acting in the opposite direction, so we have to subtract. And this is actually equal to mass times acceleration. So what we actually did here is we considered this direction to be, let's say, our x direction. And we said that the net force in the x direction is equal to mass times the acceleration in the x direction. So what I wrote above is basically that Newton's second law along the direction of the plane. And I think from this point, we have to find beta. And if you look at this equation, there are actually two unknowns, right? So there's beta, which is what we want to find, but there's also this tension. So to find another equation, we would need to look at the equation of motion in the perpendicular direction to the plane. And the reason we want to do that is because, in the direction perpendicular to the plane, there is no acceleration. So I'm going to call that AY, right? So that direction is going to be like this, kind of. Right, so all the motion is happening, parallel to the incline. And if you look at this pendulum bob from the outside, it will never move in a direction normal to the plane. It will always stay at the same level. So its acceleration, its velocity, and its acceleration in that direction is just zero. So that means that the forces acting on the pendulum perpendicular to the plane are equal to zero. So, or the net force, which is the net force in the y direction, is m times ay, which is equal to zero. So let's look at what those forces are. So first of all, we have this force of tension, which is t cosine of beta. So we have t cosine of beta, and the other force is this mg cos theta. So minus mg cos theta is equal to 0. And that's our second equation, and this was our first equation. So that's pretty much everything. Now we can rearrange and find some expression for beta. So we have t cos beta is equal to mg cos theta, which means that the tension will be equal to mg cosine of theta over cosine of beta. We can then take this tension and then we can substitute it back into this first equation. So that will give us mg cosine of theta over cosine of beta multiplied by sine of beta. So multiplied by sine of beta, and then minus mg, and then we have sine of theta. And this will be equal to just mass times acceleration, right? So now we just have one equation with one unknown. So we can simplify some things. We can cancel out the m's. And then hopefully you'll notice that this quantity here is just tan of beta, which means that beta appears just once and we can make it the subject of our equation. So if we keep this term on one side, we can take everything else on the other side. So we have a plus g sine of theta, and then I'm going to divide everything by g cos theta. And this will give us just tan beta on this side. and then this is equal to A over G cosine theta plus tan theta. And at this point, you're pretty much done, but if you want, you can write that beta is the arctan of tan theta plus A over G cos theta. And that's what the angle beta is going to be in this case, and that's the end of the question.